Hey guys, welcome to part 2. So what we're going to do is we're going to finish off this. We've only 3 experiments left to do. So we have the momentum experiments, and then we have the Boyles Law experiment, and then we are finished. Okay, so there's not much here to do. Okay. Now, so the very first thing we're going to do here is to show that acceleration is proportional to the force that causes it. Okay. So acceleration is proportional to the force. So basically, your diagram is this. Again, guys, simple diagrams, nice and neat. You have your weight hanging over the side, your trolley with the weights on it, and your ticker tape timer or your light gates or whatever. Okay, all right. Now, set up the apparatus as shown in the diagram. Start by taking one weight from the trolley and add it to the other at the hanger at the other end. Note the weight at this end. So notice you keep noting the weight that's on the hanger. Okay. Release the system and allow it to accelerate. Okay, and then repeat that. Okay. All right, so you keep repeating it, you do it a few times, get an average, and you keep taking a weight and putting it here and do it again, take a weight, put it there, do it again. You just do it over and over and over and over and over, okay? And then, of course, we draw a graph of the force on the y-axis against the acceleration on the x-axis, and the slope of the graph corresponds to the mass of the system. So we can calculate the mass of our system, okay, from this. All right, so your initial velocity, your final velocity, your time, okay? So your initial, initial velocity is what speed were you early on when you pass the first light gate, and what speed were you when you pass the second light gate, that kind of thing. That's what's kind of happening there, okay? And then, of course, your acceleration is v minus u over t, and then you can calculate your mass from that. So this is the mass minute, really, here, okay? The mass in grams, okay? Actually, no, you can't do the mass minute here. F equals ma. Yeah, so you could do a mass minute, F equals ma, get the mass of the... so you have the force from the weights hanging off. So you could calculate the force of the weights hanging off here, you see. And F equals ma. But don't do the mathematics, guys. They like to see the graphs. Okay? So the graph is the force divided by the accelerator, or force on the y-axis and the acceleration on the x-axis. Okay? And y, well, F equals ma. Y equals mx plus c, but there is no constant here, so it's y equals mx. So therefore, F is on the y-axis, A is on the x-axis, and our mass then. You see? That's how you get it. All right? Does that make sense? So there you go. That's how you get it. Okay. Our conclusion, our graph results in a straight line through the origin, verifying that acceleration is proportional to the force predicted. The slope of our force graph was yada yada. So you have to get that yourself. Okay. Now a few things here. There's a lot of background information here, if you will. Okay. So here, when adding weights to the hanging mass, you must take it from the top of the trolley. Okay. There were a common question. Do I have it down here? I don't, but I'll explain it here. Okay. All right. There it is. Yeah. Why must the hanging weights be taken? That should be a why. Must the hanging weights be taken from the top of the trolley, okay? So that the mass of the system is kept constant. So the system is the whole thing. It's the trolley plus the weights plus the thing hanging off the side. So if you're adding weights from outside, that'll skew the whole thing. It has to be from one to the other. You see, you have to keep the system constant. Otherwise, it's going to go wrong, okay? All right? And then, of course, the usual, ensure the runway is free of dust, ensure it's tilted slightly, okay, to allow acceleration. The usual things there, okay? So that's the main question here, guys. Why is it kept from the system? Because you have to keep the mass of the system constant. You can't be taken from external sources, okay? I love when that happens. Okay. Yeah, so this kind of explains it, guys, in more detail, you know. That's generally your answer, but if you want to read more, you can read more today. You have the notes online, okay? And then the ticker tape system, which we won't be using, we'll be using the light gate system. Okay. Now, this one hasn't come up in a while. I don't think it's going to come up though. I think this year it's going to be. It could be. Boyles Law hasn't come up since 2014, 15. I think that could be the one. But anyway, to verify the principle of conservation of momentum. Again, conservation of momentum. You have your two trolleys. That's your diagram. Okay, and your Velcro. For us, it's magnets on the front of them, but it's all the one. Okay. Once you indicate in your diagram how are the two trolleys going to stick together? That's key. They will get marks for that. Setup is shown. Track is tilted. Note the mass. They're both at rest. One is given a push until it collides with the second one, where they join together. Use the ticker tape to calculate the trolley of collision. Repeat, adding mass from one trolley to the other. So you just basically move the weights from the first one to the second one. Yada yada. Okay. Now your calculations. Then you do 3 or 4 times. So for before, these are all going to be 0 because trolley 2 isn't moving, you see. So trolley 2 isn't moving, so it's always going to be 0 in the before, okay? Anyway, so what's the mass of trolley 1? What's the speed of trolley 1? And then add them together, okay? So it's basically just this, right? After, okay, it's basically what was the mass of trolley 2, the mass of the 2 trolleys stuck together, and then the speed of the objects, the 2, because they stick together, so they become this. It's this equation. M1 U1 plus M2 U2 equals M1 plus M2 over V. That's the equation, okay? Because they stick together, the mass is combined, and then the speed is the same. That's the equation that we're looking at here. So you're just putting the values in one after the other. That's all, okay? For your calculations, for each run, calculate total momentum before and after, okay? The momentum should be equal to momentum after. So now there will be a slight difference, guys. Obviously, the way the trolleys work is they should be identical, but they're not, because when they crash, they give off energy in the form of sound and things like that. So they won't be exact, but they'll be close. That's the key here, okay? Obviously, leave your conclusion gapped. Oh, God almighty. Leave your conclusion gaps. Don't leave anything there. Leave it blank. Just fill that in later in our own time, okay? Sources of error. The usual runway is free of dust and tilted. And then they might ask me before they asked if it was an air track, okay? So they said, well, in that case, you don't have to account for friction, okay? Now, I have an air track, actually, but it's actually handy to use, but it's not great. The light gates don't work. Right, so the last experiment then, the one that I think could possibly come up, because it hasn't come up since 2015, all right? So come up in 2021, and if not for 2021, for 2022, is this one, verification of Boyles Law. So that's your apparatus, okay? Now, Boyle was an Irishman. That's why they used to ask this question all the time, and then they stopped because it became too predictable. So I think it's time it came back in. So you have your fixed mass of gas, your oil, your pressure, your air coming in, and all that, okay? All right, so that's your Boyles Law apparatus. Your procedure, setup is shown, open the tap and pump the oil out as far as possible until the gauge reaches maximum reading, okay? And then close the tap, okay? Wait a few minutes before reading the pressure and volume. Open the tap slightly, the pressure falls to a convenient read. In other words, you drop the pressure to 10 pascals so you can see what the volume is. That's the idea, okay? Now wait and then repeat, okay? Pressure is going to be on the y-axis and 1 over V on the x-axis, okay? All right, so 1 over V. Right? If you remember, pressure is equal to 1 over V. That's Boyles Law, log tables. Go to the log tables, okay? This experiment is very easy when it comes up. Pressure, volume, 1 over V, pressure times volume, PV, okay? Because pressure is proportional to 1 over V, okay? Hence why the two together are PV. If you remember back to that topic in the videos, okay? All right, so why is pressure, even though we control pressure, why is that on the y-axis? Well, actually, you can control the volume as well, but it's much more difficult. So a lot of times people just control the pressure, all right? Do I have the calculations? Oh, yeah, all right, so I don't have the calculations there, but I can show you. All right, so the calculations aren't there, but the reason is that P is equal to K 1 over V, K being the constant, okay? So K is equal to PV, all right? Now, the reason we do it that way is that if you do y-axis, y2 minus y1 over x2 minus x1, what you'll get is P over 1 over V. And if you have a fraction below the line, that comes above the line. So therefore, PV. You see? That's why. That's why we put the 1 over V on the x-axis. It's going to be below the line, and if you have a fraction below the line, it gets pulled above the line. Does that make sense? So therefore, that's why your slope then, therefore, K equals slope. There you go. That's it, okay? All right, so that has to go back to Boyles Law for that, but that's why we put the V, the volume, on the x-axis, okay? All right, because it's inverted, it's 1 over V, and therefore you'll have to pull it above the line so it'll flip around and become the correct thing which you want, which is PV. Always go to the log tables and the equations and make your graphs fit those equations, okay? Now, key things here. Precautions, wait a minute for the temperature and therefore the volume to stabilize after the pressure. Because when you change the pressure, the temperature changes and that affects your results. Have your eye level with the pressure gauge when taking readings to avoid parallax error. And work in a room when the temperature remains constant. That's fairly easy enough in the classroom, okay? So when you're doing your results, you should find that PV in the final column is always the same, okay? This verifies that P is inversely proportional to V. And you get a straight line through the origin, okay? That's kind of generally it, all right? There's not much more there. It's very straightforward, guys, very straightforward, I'm serious. They give you pressure, they give you volume, just change the volume to 1 over V. You could even do your maths here first to check that you're right, and then if you are, plot your graph, and you get a straight line through the origin. And that's it, okay? It's very easy, okay? Common question, and this is why it's easy. In Boyles Law experiment, how would you make sure the temperature remains constant? Allow time between readings. If the pump was disconnected and the tap is open, is there any reading? Of course there is the pressure. That was a question 1 year, a lot of people couldn't answer it. So if we take the pump off and we just leave it open, is there going to be 0 read? What's the reading going to be? It's going to be the atmospheric pressure because it'll still read the atmospheric pressure. And that's it. So that's part 2 finished. That's all the mechanics experiments covered, okay? If you have any questions, leave them on the Teams page or ask them in the comments section below. All the best.